Okay, let's get to work on another problem. So in this problem, we have a 1.11 microcoulomb charge and a minus 2.22 microcoulomb charge. They're held at rest, separated by 10 millimeters. Let's draw a picture as we get started. So here's our Q1. And here's our Q2. Q2 is bigger than Q1. And they have a distance between them are 10 millimeters. In our calculations, of course, we'll put that in meters. Find the electric potential energy of this configuration of charge. So we have two charges. It's an interaction between two charges. The electric potential energy is K times Q1 times Q2 divided by the distance between 1 and 2. Put in our numbers, 8.99 times 10 to the 9 newtons meters squared divided by coulombs squared times charge 1, 1.11 times 10 to the minus 6 coulombs. Remember, we include the sign of our charges, so times negative 2.22 times 10 to the minus 6 coulombs divided by the distance between the two charges, which is 10 times 10 to the minus 3 meters. So our electric potential energy between charges 1 and 2 is equal to negative 2.2153 joules. This problem has a bit of calculation, so I'm just going to hold on to a couple of extra sig figs. If you were doing this on an assignment or a test, it's probably fine around a 3 sig figs here. Okay, part B is different. In part B, a negative 3.33 microcoulomb charge is placed at 10 millimeters from the original two charges. So where is that going to be? It's going to be 10 millimeters from this charge and 10 millimeters from this charge. So it must be on the point of an equilateral triangle. So here's our new charge, Q3 equals minus 3.33 microcoulombs. It's bigger than those two. The distance between them is that same R equals 10 millimeters. And now we have a new question. Find the electric potential energy of this new configuration of charge. So when we have systems of charges, we have to add up to get the total electric potential energy. We have to add up the electric potential energy between each combination. So charges 1 and 3 have a potential energy between them. So K times Q1 times Q3 divided by R. And Q1 and 2 have a potential energy between them. We already found that out. Q2 and 3 interact, so they have a potential energy, K, Q2, Q3 divided by R. So those are all of our different possible combinations. So we find the energy between these two, the energy between these two, and the energy between these two. We add them all up, and that gives us the total electric potential energy. Okay, so when we have multiple charges, the total electric potential energy is equal to the sum of all the individual electric potential energies. So electric potential energy, we say IJ, it shows that we're going through all the combinations. In this problem specifically, UE total equals the potential energy between 1 and 2 plus the potential energy between 1 and 3 plus the potential energy between 2 and 3. Okay, let's find each of these values and then we'll add them up to get our answer. The electric potential energy between 1 and 2, that's easy, we already found it. The electric potential energy between 1 and 3 is our value K times Q1, 1.11 times 10 to the minus 6 coulombs, times Q3, negative 3.33 times 10 to the minus 6 coulombs, divided by the distance between them. That gives us a total electric potential energy between 1 and 3 of negative 3.3230 joules. Okay, between 2 and 3, same form, K times Q2 times Q3 divided by the distance between them. Q2 is negative 2.22 times 10 to the minus 6 coulombs. Q3 minus 3.33 times 10 to the minus 6 coulombs, divided by the distance between them, which is 10 millimeters again. That gives us a total potential energy between charges 2 and 3 of positive, remember those are both negative, so we get a positive potential energy, 6.6456 joules. To get our total electric potential energy now, we add up these three numbers. What we get for our answer is 1.1076 joules. So that's the total electric potential energy between these three charges. Okay, part C now says the negative 3.33 microcoulomb charge is released, so we let this one go and it's allowed to move freely. First thing we're asked to do is to describe its motion. So how does it move? Well, hang on, let's just grab a fresh piece of paper. Let's draw a new picture here, and let's think about how is it going to move. So we've got our positive charge, Q1 right here. We've got our negative charge, that one's twice as big. I'm going to draw two negatives in there, Q2 right here. And we've got our third charge, Q3 down here. That's 3 times as big as this one, so I'll put 3 negative signs here, Q3. If we want to think about how it's going to move, it says describe its motion. Perhaps the easiest thing to think about would be the forces, because a force is something we understand. So between Q1 and Q3, those charges are opposite. It's going to be an attractive force. So I'm going to draw the force by 1 on 3 is towards Q1. My force between 2 and 3, they're both negative, so it's going to be a repulsive force. Q2 has a bigger magnitude than Q1, so the force by Q2 on Q3 is going to be a bigger force. So it's repulsive and it's bigger. F2 on 3. When we do the vector sum of these two forces, the direction we're going to get for our net force is definitely going to be to the left, and ultimately it's going to be a bit down. So I'm just doing a visual sort of addition of those forces now. So there is our net force. So the net force is down and left. What does that mean about the motion? Well, it's going to move down and left. So it's going to move in the direction of the net force. So to answer our question for part C, to describe its motion, Q3 will move away from the two charges Q1 and Q2 because of the net electric force on them. Okay, what's the next part of question C? Find the work done by the electric field during its motion. So for this bit, we'll remember that the total work done is equal to the negative of the change in potential energy. So the work done by the electric force, the internal force, is negative of the change in the electric potential energy. Change in potential energy would be U final, subtract U initial. So we have to think about what is U final and what is U initial. U initial is pretty easy. So initial is when Q3 is right here. We've already figured that bit out. U initial is when the three charges are here on this triangle. That was the number we found in part B, 1.1076 joules. 1.1076 joules. What about final potential energy? So where does charge 3 end up? Well, it's being pushed away by this force. It's going to end up far away. Q3 is going to get pushed away. It's going to move away and away and away. UF is when Q3 is, put this in capital letters, when it is far away. What does far away mean? Well, it means it's a big distance away. So U13 would be K times Q1 times Q3 divided by R13 final. Well, this is far away. This is a big number. So this potential energy is about 0. And likewise, U23 will be K times Q2 times Q3 divided by the final distance between 2 and 3. This final distance is going to be a very big number, so this final potential energy is going to be a very small number. That means that our final potential energy of the system will then just be the potential energy between charges 1 and 2. So UF is UF of 1, 3 plus UF of 2, 3 plus UF of 1, 3, oops, 1, 2. 1, 2 didn't change. So that final potential energy is minus 2.2153 joules. They're still held in place, so they didn't change from part A. Okay, let's put all of this together. So our work done is negative our change of potential energy, UF subtract UI, equals negative of a negative 2. Be really careful with all your signs here. Brackets are your friends. Subtract 1.1076 joules equals positive 3.3229 joules. Okay, part C also says discuss the sign of the work done. Well, our work done is positive. We can see that. Why is the work done positive? Well, the force is in this direction, the displacement is in this direction. So the work is positive because force and displacement are parallel or in the same direction. So the electric field will do work to move that charge out of the way. Okay, there's one more bit to this problem. Find the final speed of the 3.33 microcoulomb charge, negative, if it has a mass of 3 milligrams. So we said Q3 was going to move far away. It's going to be over here somewhere. How fast is it going? So that's where we'll use our conservation of energy to solve it. So let's just do a little sketch of our problem. So in the initial situation, we've got our 3 charges right here. So Q1, 2, and 3. In our final situation, charges 1 and 2 are here, but charge Q3 is all the way over here and is moving away with some speed VF. Okay, so this is our initial, this is our final. It's far away and it's moving away at some speed. Let's apply our conservation of energy. Final total mechanical energy is initial total mechanical energy plus work done by non-conservative forces. We don't have any non-conservative forces, so that bit is equal to 0. Our final potential energy is K final plus U E final equals our K initial plus U E initial. Let's see what we know for each of those things. K final is 1/2 times mass of charge 3 V final squared. So over here on the side, just so we don't clutter up our equation too much, K final of 2 equals 0. K final of 1 equals 0. Those are held in place. They were never moving. Our final electric potential energy, we already found that bit in our previous problem. So we found that our U final was minus 2.22 joules. So minus 2.2153 joules equals K initial. Well, what about K initial? K initial 1 equals 0. K initial 2 equals 0. Those were held at rest. K initial 3 also equals 0. It was released from rest. So our K initial is 0. Plus our UE initial, we found that in part B. So our initial electric potential energy was this much right here. Okay, so that gives us 1/2 times M3 times VF squared equals 1.1076 joules. Take this to the other side, plus 2.2153 joules. Our VF then is going to be 2, we'll add these two numbers together, 3.3229 joules divided by mass 3. Mass 3 was 3 milligrams. So this is 3 times 10 to the minus 3 grams. A gram is 10 to the minus 3 kilograms. So 3 milligrams is 3 times 10 to the minus 6 kilograms. Then we take the square root of the whole thing to get a final speed of 1488 meters per second. So that's how fast charge 3 is moving when it gets away.